Yes, we can.
Yes, yeah, thank you for letting me know, guys. I would have gone right through to the end and never would have known. So, okay, hold on. Right, okay, yes. So NNL, so we sit between industry and academia, and our main goal is to sort of take the R&D that's been done at universities, nuclearise it, and then deploy it within the UK nuclear sector. Essentially, we work like a scientific consultancy, so commercial customers will come to us with a particular challenge, and then we undertake the research, development, and all the kind of the background sort of science that is required to then deliver a solution to that particular challenge. So my particular area is computational fluid dynamics. So I'm based in our Warrington office over in Chadwick House. So that's one of our facilities where everything's desk-based. We also have a couple of experimental facilities, so one in Workington, one up in Sellafield, and they're able to do lots of large industrial scale experiments, which include sort of radioactive hot cells as well as non-active facilities in Workington. So as I mentioned, my background's in thermal fluids, and this is quite a special area in the nuclear sector. And this is largely due to the kind of materials that we deal with in heavy plants which process them. So obviously, there is a requirement for us to process, store, and safeguard nuclear materials. They're hazardous. Because of this, we tend to have developed over the decades large industrial facilities for carrying out various activities on these nuclear materials. Because of the nature of the materials we're dealing with, you can't always go in and have a look, see what's inside. It's almost impossible to sample or to make direct measurements. And so this is where we tend to use modeling and simulation to provide some insight. So there's a good example here. So this is what you can see is a highly active storage tank. So these were commissioned in the 70s, this particular model, and they contain a liquid waste, which is produced as we reprocess nuclear fuel. It's highly radioactive and it contains a solid, but there's also like a sediment within it. Now the sediment settles into the base of the tank, and because it's very radioactive, it generates heat and causes corrosion. So it's very important for us to know where the sediment is, because that then tells you where the thin spots are in the base. And we can use information like that to predict how long these vessels will last. So this is at the very bottom here, this little animation you can see is an SPH calculation, which was actually undertaken in one of the PhDs that we did, where we were looking at this sediment motion process. So what this is, it's called a jet ballast, and it's a little sort of pulse jet actuator. And the idea is that this squirts a load of fluid and agitates the solid and stops it from forming hotspots. So yeah, this is one of the sort of R&D projects that I mentioned earlier. So we tend to use modeling simulation in a lot of different use cases. One of the main ones is underpinning safety cases. So this is a regulatory requirement for nuclear operators. If you have a nuclear plant, you need to prove that it's safe. We are able to obviously simulate scenarios that you can never try and practice, such as things overheating or catching fire or shutting the ventilation off in a large industrial facility. So we can simulate these and then we can provide guidance to our customers as to how they can continue to operate their plant safely. Another one is the optimization of activities. So this is another big one where a customer might come to us and say, look, we're operating this way. We feel we can probably get more efficiency out of the system. Can you help us? Can you use simulation to try and improve the efficiency or the throughput of this particular plant? Another one is obviously, given the scale of the facilities that we're looking at, any experimental work, especially if done to scale, can be very expensive. And the materials that we're dealing with obviously can't always be used. You can't obviously have radioactive materials and some of the things that we're trying to simulate. So you couldn't capture that in an experiment. So what we offered here is a much more cost-effective way of providing insight into complex systems. So I thought it might be useful just to sort of briefly cover some of the tools that we use. As you'd imagine, being a commercial organization, we tend to use sort of industry standard codes and pieces of software. So in my particular team, we do computational fluid dynamics and thermal modeling. Our core tools would be the ANSYS suite of packages. Recently, we started using Star CCM because it's particularly good in terms of multi-phase. In terms of our analysis, as you can imagine, we deal with very large amounts of data. This could be measurements from plants to anything such as a weather report or experimental data, which has been captured off one of our rigs. So we've also developed a suite of kind of analysis tools in Python, R, and MATLAB, amongst the main ones. We also develop some bespoke capabilities in the commercial modeling software. So if we find that the commercial tools don't necessarily work out of the box, we do have quite an active development team who can build in new functionality to these commercial packages. Probably of interest as well is our computational resource. So until now, we've been working on a legacy HPC system, which I believe was commercial grade hardware and consisted around 1,000 cores. So this is coming towards the end of its life now, and we're planning a new hybrid system, which will be a mixture of on-premise HPC as well as cloud-based resource. Obviously, working in the nuclear sector, we have certain security restrictions. And so this system allows us to maintain the security that we need, have an accredited system that ONR are happy with, but also where projects are perhaps less sensitive, we can farm that work out into the cloud and sort of allow that computer resource to sort of grow and shrink as required. So there are some practical considerations for the type of modelling that we do, and I thought it would be useful to really cover these because this is where the potential benefits for these big exascale systems really come to the fore. One of the main ones for the type of work that we undertake is uncertainty, and a lot of this is to do with the history of the nuclear sector. So there's a good example here. You can see a tank being lowered into an underground vessel. So this was, I think it was 1950s, 1960s. This is another type of waste tank. Now, the original drawings for this, the original data might not be available or might not be legible or might be hard to find. And so often if we're trying to model something, we often have very limited data to go on. Also, the materials that we're dealing with themselves are subject to change. So we may have a process liquor, say, which changes through time due to chemical reaction or radiation damage or some corrosion of something else in the vessel. And so there's often a bit of uncertainty that goes into the model. This is something we tend not to explore because obviously when you start mapping out the effects of uncertainty, it tends to rely on lots and lots of models, and it's just, there's too much computational overhead there. Another key issue, again, I'm going to touch on this shortly, is we are very often called upon to resolve very small details in an otherwise very large complex system. And I'm going to show a really good example of this one in just a little while. Another issue is one that's becoming more and more common, is the need to explore quite a large parameter space. So this might be a case where a customer comes to us and they're interested in an optimal configuration of, say, loading heat within a fuel store, or coming up with a worst case scenario to verify that something's going to be safe. So these tend to involve lots of simulations, often involving many parameters which can change. And again, there's a significant computational requirement there. And so we have to, over the years, we've had to work out some workarounds for these that allow us to do what we can with the limited computational resources at our disposal. And finally, because we are effectively a technical consultancy, our customers come to us because they need us to help solve a problem or to improve something, and the data we give them directly affects things that happen on nuclear plants. So at the end of the day, what we're really doing is giving our customers something that tells them which buttons to press. And so there is obviously a timescale associated with that. If they have activities that are planned, then we need to make sure that we can deliver a solution to them within a very timely manner. So as I mentioned, over the years, we've come up with a range of pragmatisms that are probably quite familiar to anybody that's worked in sort of an engineering field. However, it's probably useful going over these because they are areas where we could potentially alleviate some of these challenges using larger scale computing. As I mentioned earlier, uncertainty is a real problem for us. So we often aren't entirely sure what's in some of these vessels in terms of the properties. And obviously, if you're trying to predict something like a temperature, that information is really important. So what we would tend to do is we'd have a bit of a survey before we start a job, and we try and assess the materials and the data that we're dealing with. And we tend to introduce a very large degree of pessimism. So a good example of this is if we're modeling, say, a fuel store. So radioactive fuel generates heat. And often we know that a particular package may contain, say, between 1 and 10 watts of energy. So, and the basis of the modeling, what we do is we'd assume then that all heat packages within a particular facility have 10 watts of energy. That then overpredicts the temperature, but what it does is it kind of builds in a bit of a safety margin. The negative consequence of this, I mean, it means that any simulations we do are going to provide safety because we're over predicting temperatures, and then the system can be designed to accommodate those. That, however, comes at the cost of over engineering some systems, and in some cases it might actually stop plant activities which are safe, but because of the degree of pessimism that's been built into the model, it means that activities have to stop, and we then need to review the work. A really common one is that the systems are just simply too large. Obviously, with the computational resources we have, there is a limit to how much resolution we can build into our model and the types of complex physics that we can build in. A good way of tackling this is to use system level codes, such as sub-channel codes or lump parameter methods. The obvious disadvantage there is that these techniques tend to be based on sort of engineering level calculations or correlations. So they're a step above hand calculations, but you do lose a lot of the detail that may be important. Also, the models themselves can become invalid as you start moving away from the system for which the correlation was derived. Another one that's really key, and it's becoming more important for NNL, is the high degree of coupling. So we've recently started moving into reactor thermohydraulics, and for say a water-based reactor, the interaction between the water and the neutrons coming out the fuel rods is very important, and there's a lot of coupling between those two. So there's feedback, the water acts as a moderator, its ability to moderate depends on temperature, and so there's this coupling between the neutrons being released and the water moderator. To tackle these problems, we might link, say, a lumped parameter code with something like CFD. That's good, it gives you a broad feel for the system, but again, it's a way of kind of missing out some details which might be important, especially if you're trying to optimize something. And finally, the delivery with which we have to satisfy our customers. So the delivery timescales there are often influenced by what's happening on plant, and there's not much wiggle room in those. Nuclear projects are, just by their very nature, very complicated, and so delays in one engineering process can have significant upstream effects, downstream effects rather, and so we really have to make sure that we can deliver our results to customers in a timescale that's useful for them. So this naturally means if those timescales are tight, we do have to simplify models where possible. So this is an area where we need a lot of engineering judgment, but it allows us to sort of deliver things within a timely manner. The challenge obviously being that oversimplifying the problem means we can miss something. Now, these are all areas that are largely governed by the lack of computational resources. So obviously any improvement and anything approaching exascale would really help us out in things like this. So the first case study I'm going to talk about, so this is an exotic fuel store, and by exotic, what it means is it's a non-standard fuel. So this is going to be radioactive material like pellets or little plates or fuel pins, which they haven't been in a reactor, but they have been used for experiments up in Dounreay, and they are quite radioactive. As a result, they generate heat. So what you can see on the right-hand side here is a large, it's actually a concrete vessel, and these cylinders that you can see here, these are ports. So this is the airspace, and the outer kind of wall is the concrete shell. So the flow path here, we have a green inlet, and so the flow goes in this. This is an actively cooled system, and each one of these ports with these cylindrical columns is actually a hollow airspace which will occupy a very large fuel container. So the fuel container is a cylinder, and it's about 3.5 meters tall. I think it's about 40 centimeters wide, and that contains this active material. So the purpose of this store was originally for something else, and this is a good example of the type of work we often pick up, that this facility is now being retasked to store these exotic fuels. It's not what it was originally designed for. So the fuel sits in each one of these columns, and what we have is an active ventilation system. So air gets pushed in through the green entrance, it then passes along those yellow channels along the base, and it exits through the red squares at the front. So obviously, as the ventilation pushes air past the fuel, extracts some of the heat, keeps everything nice and cool. So the query here from the customer is, what's the worst possible loading scenario for this? We tackle these problems quite a lot. Worst case scenarios, obviously something you don't want generally, but from a modeling perspective, it's what we're aiming for, because the philosophy here is if we can simulate the worst possible scenario and this facility is safe, then any conceivable configuration we're likely to find in this facility will also be safe. So the question is really twofold. What's the worst case scenario? And then given that worst case scenario, what happens if the ventilation fails? Will the fuel become too hot? And will the concrete become too hot? So will we fail our safety case if we go ahead with this planned activity? So it's a fairly straightforward problem in terms of the physics. It can be solved just with off-the-shelf CFD software. What we have is fuel, which obviously gets hot. So this is just a cut through one of those columns I showed you. Heat transfer processes are all well understood, but the challenge here is that if you recall the original diagram I showed you, that all those cylindrical ports are coupled. There's air gaps between adjacent ports, and so you can conceivably have the flow in one port affecting its neighbours and even having a long-term effect on ports that are quite distant. So there's two kind of interactions here that are important. The buoyancy force, which is coming from the heat that's generated by the fuel, that obviously warms the air and generates buoyancy. So that would be if you have a non-uniform distribution of heat load, then that'll give you a non-uniform distribution of buoyancy. And so the interaction of your vent with the buoyancy forces is strongly dependent upon where you place fuel within that assembly. So that's all very well and good. We can tackle this problem using commercial software. However, there are thousands of possible configurations, and this is made worse because we have 60 ports, but we also have 7 different types of fuel. And the fuel varies. This is a typical cross section. So the fuel comes in these cans, and the cans themselves, it's just like literally like a can of beans, like small metal can, and it contains radioactive material that's heat generating. So these are then stored in a multi-layered system. So the one that we can see here, there's like an aluminium inner liner and a stainless steel outer liner, and it's this stainless steel thing that slots into each of those columns. Now, in between those, there's layers of argon, and so the conduction path here is actually quite complicated. So if we really want to account for the heat transfer from this fuel into the outer world, we need some way of accounting for these small details, because they do have a big impact on the global temperatures. It's complicated by the fact there are 7 different types of fuel. So we've got 60 fuel ports, 7 different types of fuel, and that gives rise to hundreds of different combinations. Now, obviously, we can't run each one of those. It's a very large model. Computationally, it's impossible. So we have to sort of refer back to those pragmatisms I mentioned earlier. It's particularly complicated here, and it's not a problem that there's no symmetry, so we can't sort of take advantage of that in our models. And obviously, the interaction between your buoyancy and ventilation is quite significant, and it can become quite complex. So when we're distributing fuel across this, we've got 7 different types of fuel, each generating different amounts of heat. We need to try and work out how to position them here to get the worst possible scenario in terms of temperature. The main computational issues here are, obviously, there are a large number of cases to run. Each case is in of itself a large simulation. I think even using the majority of our HPC, we were looking at several days of runtime per case. So obviously, if you need to run several hundred, that's just not possible. And finally, if we're actually looking at a loss of cooling accident where we switch off the ventilation and then the temperatures are purely driven by buoyancy, your transient runs to hours or perhaps days. So again, it's just not achievable. And I'm conscious of time, so I will quickly go through this next case study. The next one is a HAL evaporator. So this is an example where we have very strongly coupled physics and lots of kind of feedback between different processes. Evaporators are process vessels which are used to reduce volumes of liquid waste. So the waste they contain is corrosive, it's highly radioactive. This is an example. This is evaporator C. So this came online in 1990. It's now been decommissioned, and its big brother's now in place to take over. As you can see, it's a very complex kind of set of furniture inside the vessel. It's a very large vessel. So it's one of those kind of cases where in safety, it's a bit of a nightmare because we have to resolve some very small details. The furniture really matters here in terms of controlling the flow direction. So we need to be able to account for this in our models. The problem becomes a bit worse when you consider the physics as well, because it's a very complex set of physics we have to deal with. So the evaporators are steam heated. So there's just a slice through here. What we have is a vessel with a hollow outer wall called the jacket. The liquor goes on the inside, and then we have this kind of void space above. So this ullage is maintained at a low pressure, subatmospheric pressure. The idea is that if there's ever a breach in containment, things are sucked into the vessel and not squirted out. It also suppresses the boiling point of the liquor. So the aim of this vessel is to boil this off, and this is done by flushing steam into this outer hull. The steam then condenses, and that condensation generates a lot of heat. So it's that phase change that powers this. So in this case, I've only considered the outer jacket, but the same thing's going on in a series of 6 coils which run through the vessel. So the heat increases the temperature of the liquor, and eventually the liquor starts to boil. We're able to suppress the boiling point of this because of the partial vacuum in the ullage. What this does is it reduces the volume of liquor, and it means it's more suitable for long-term storage, much more cost-effective. What happens, though, is this is a very long process, so it lasts for several weeks. So again, the simulation timescales on this are enormous. But over time, because the concentration of this liquor increases, we continuously add more and more liquor, the heavy metals start to precipitate out. So what happens is the gas that gets given off, that gets taken away, that's not radioactive, that gets processed as a separate waste stream. And what we can do is we're condensing down the radioactive materials in here. It then starts to form a sediment which sits on the base of the evaporator, and it leads to a local increase in metal temperatures. So this enhances the corrosion, and it's something that we need to predict through modeling. So it's one of those cases where it's a very strongly coupled system. This sediment forms almost a thermal blanket. It provides a thermal resistance to stop the flow of heat going into the vessel. So that leads to local temperature increases. There's then the interaction between the flow. So the boiling process obviously generates a flow within the vessel, which interacts with all that furniture. And so from a modeling perspective, it's very much kind of a nightmare scenario. So in this case, the challenges are we have multiple flow regimes simultaneously. Some parts the evaporator are boiling, some parts aren't. Convection rules in some parts, boiling dominates in others in terms of controlling that metal temperature. We have condensation, so we have part of the process is going from steam to a gas. We have, sorry, beg pardon, going from a gas to a liquid. We have boiling, so the liquor is going from a liquid to a gas. We have precipitation, and then we have a combination of, you know, the sediment that gets deposited in the vessel as well, combining with the flows and the boiling process. Very, very complicated. So the main challenges from a computational point of view are obviously resolving this very complex geometry, trying to capture these incredibly complicated and coupled processes together, and also the long transients, which in this case, you know, days, perhaps even weeks, in this large engineering vessel. So just to briefly summarize, there's definitely kind of scope for exascale computing enhancing the work of sort of engineering modeling people like myself. It allows us to do more complex simulations more quickly, and that's good. I mean, my job as a scientist, my customer doesn't pay for runtime, so they want to pay me to do the science and do the sort of investigations necessary to solve their problems. The less time I spend looking at residuals, the better. So, you know, from a purely selfish position, it's, you know, it'd be a great thing. It also allows us to account for uncertainty in some of our models. It's something that we tend not to do as a general rule. We simply don't have the computational capacity to run many models and then generate an understanding of the uncertainty in the system. Also, we, as part of NNL's remit, we develop new products and new services, and at the moment we're starting to move into the area of machine learning and artificial intelligence. So again, this sort of computing resource, obviously these techniques are incredibly power and data hungry. So having something like exascale computing at our fingertips would obviously be an enormous kind of help there. And then I think finally, I mean, it's the key thing really is the high fidelity multiphysics. It's going to allow us to take these really complex problems and actually simulate them, where at present it's really not possible to do a full account of them. Okay, now that's I think you've heard enough from me, guys, but I'm more than happy to field your questions.
Thank you very much, Brendan. That was very interesting. I'm glad we were able to see your slides because there was a lot on. So we've got some time for questions on this. If anyone wants to put a question in the chat. Okay, I did have one sort of question. You make quite a point about some of the details of these applications really not being captured by the current sort of modeling strategy. One question, I guess, is will exascale computing actually allow you to capture these details and sort of avoid some of this pragmatism? Do you actually think that's possible with exascale computing?
I think in some cases, yes. There's always going to be some engineering pragmatism that comes into the models, but what it would allow us to do is to get a little bit closer to the details that we just can't capture now. So the example I mentioned earlier of the fuel store, we really had to come up with some really innovative ways of trying to solve that problem, because that was one of those cases where the customer needed an answer very urgently. So if we'd had access to more computer resources, we certainly could have refined our models better and probably come up with a better solution.
Okay, yeah. So
yeah, I think it's a mixture of other things as well. It's as I mentioned, we have experimental facilities. So some of the physics that we're trying to deal with, there isn't actually a model for it yet. So low pressure boiling is a really good example. So in the evaporator case, there's very little published data out there on low pressure boiling. It's really hard to get information on that. So what we can do is use sort of a mixture of experimental results and combine it in with that. So I mean, I'm guessing in terms of deploying those models, yeah, exascale computing would really give us something there. And if you consider, say, the resolution we'd need to capture the sediment and boiling at the base of that evaporator, we just simply don't have the resolution just now. So we're looking at more kind of approximate methods.
Well, and in fact, I mean, when you look at the length scales involved with sediment and with boiling, I mean, even exascale would be a challenge even with exascale, I suspect.
Yeah. I think one of the main...
I was going to jump in. Can I just jump in a moment?
Of course, yeah.
The interesting thing, Brendan, is to what extent do you try to have multiple different scales in the simulation? So is the simulation all trying to run at the same scale, or is it very adaptive?
Oh, I think normally we would tend to have it at the same scale.
Because this is essential in our cosmology work.
Yeah.
We couldn't just get anywhere if we didn't do that. It strikes me you've sort of got a very similar problem.
Yes, I think there is an element of that in some of the problems that we deal with for sure. I mean, one I sort of touched on in the slides but didn't really talk about was laser spectroscopy. So this is one where we have actually been considering using SPH. So it's a very violent process where you fire a laser at it's a piece of metal, and then it generates a plasma, and you can infer from the spectrographic data that comes off that what the metal's made of. So it's obviously got lots of applications in nuclear. There are some weaknesses in the approach which aren't fully understood, and it's believed that so as you drill into the metal, if you fire a few pulses, you can actually deposit contaminants inside the metal which shouldn't be there, and so it can lead to inaccuracies and false readings. So we'd be interested to try and simulate something like that with SPH. What actually happens is there's multiple different timescales there. So the laser pulse itself might last for a few nanoseconds, but the whole kind of interaction of ablating the material, the interaction with the plasma, receiving the signal, that probably happens in microseconds. So I think, for problems like that, we certainly need to consider all those different timescales, because if you've got some things happening in parallel and some in series. So it very much depends on the problem. But for most engineering calculations I come across, it tends to just be a fixed timescale for most things.
Okay, thank you very much. I don't see any questions in the Q&A, so